by the photosphere and upper convection form. So we want to have enough resolution capture granulation, and for the MURaM code, it means roughly 192 kilometers horizontal grid space, and that limits kind of how far we can then go to main size before this just becomes too expensive. In all these simulations, there's a quiet sun reference, and the quiet sun in these simulations actually is a self-consistently maintained small-scale dynamo. So the quiet sun magnetic field we don't have to put in, it's maintained by the simulation itself. And the consequence of these type of models, there's no explicit corona heating model here. It's the photospheric magnetoconvection which produces the Poynting flux that maintains the corona. The only degree of freedom you really have is what is the magnetic field structure you put in the photosphere. That is how you distinguish quiet sun from active region or anything in between. Energy is dissipated through numerical diffusivities, but since energy is a conserved quantity, these numerical diffusivities, even though they're unrealistic, they only can dissipate energy which is there. And that brings you back to the Poynting flux, which is captured by MHD. And with regard to waves, there's also no wave driving in here. Whatever is in there is just naturally excited by photospheric magnetoconvection. So in the past, what has been done with these simulations is that people actually looked at the photospheric waves and tested even seismic methods. And that has been done quite extensively over the last 10 years. Here I just show a K omega diagram, which is just based on the wave field at the optical depth 10 to the minus 2 level, which roughly mimics where HMI and instruments like this typically observe. And this K omega diagram is close enough to solar so that people who do low peer seismology or like Doug Brown, Aaron Birch, they can just use this as if it comes from HMI and just apply the geoseismic method to it and test them or where they actually can infer subsurface flows. There have been recently some studies also looking at chromospheric waves. You can also ask more here. And recently also looked at some aspects of that. But I want to now focus on the four corona setups. So I mentioned that we have magnetoconvection in the photosphere, and this is just an example of how a large-scale quiet sun model looks like. And this magnetic field you see in here, that is maintained by a small-scale dynamo. That is not something you have to impose. The simulation just maintains this against ohmic decay. And then when we have a quiet sun corona model, all we do is we just add a corona on top of this. And it roughly looks like this. This is synthetic AIA emission computed now from a quiet sun model, which is self-consistently driven by the Poynting flux, which is created by the small-scale dynamo in the convection zone. And you see all these small brightenings here, and people have recently looked more carefully at them, and they are related to the campfires, for example, people found in solar orbit. It's these low-lying Rempel connection causing them. This is how the same simulation looks on the side, and the lower panels here actually show a running difference image now of the AIA emission, and you do see some propagations here of various disturbances. Sometimes you also see some reflections which travel a bit down, but that's an artifact from the top boundary, which is not really transmissive to waves. And Feng Chen, who did these simulations a while ago when he was actually a postdoc here at HAO, he also looked here at some time slice plots and how these disturbances travel with height, and the blue lines here correspond to sound, the sound travel time, and the green curved ones to alpine wave timing. And you see these disturbances are some combination of sound waves and alpine waves. And we haven't done a very detailed analysis of this just by eye. You see mostly upward jumping stuff, but I guess somebody would have to look with a careful filtering of these wave modes to really establish their details, and if there's also a down or traveling component in there. Since this is mostly a closed field region, still it's quite sun, but most of the magnetic field is actually closed inside the simulation domain.
What are the kind of the flatter slope ones?
You mean the ones which curve over? Or what do you mean?
They don't seem to be fitting either of those curves.
Yeah.
the kind of flatter, like around 60 to 80 megameters. And 20 to 40, I think, speech to them. Yeah, exactly. So,
I mean, sometimes there's also something like some small scale mass ejection in the quiet sun. Could be something like
or
that.
little jets.
Yeah, they do exist sometimes.
So is this keeping line of sight integrated, emissivity weighted, intensity? What do you?
Yeah,
show
so
there?
this is, yeah, the A is intensity, and then here they kind of see that this is one of the horizontal velocity components, and the B here it's pressure, and the panel D is one of the horizontal magnetic field components.
But is that a cut in the plane of the sky that's here, or is that a line of sight? This is a line of sight I'm from even here, so. Steve, I think that's what you're
Yeah.
asking.
That's a good, I have to look back, but kind bit here exactly. And obviously the intensity has to be kind of integrated to the volume. The other ones are, yeah, I don't know any. I have to check that.
How are you connecting the right ones to reconnection? Are you giving some sense of or I guess that's the way probably that you're creating our own is
I mean, it's kind of, you mean something like the one? Yeah.
So is that a concentration density, or are you saying that's actual heating from magnetic reconnection? How are you?
I mean, the two are somewhat related. You have reconnection happening, and then you have kind of in the response increase of the density due to chromospheric evaporation.
Yeah, so I guess how does your code show reconnection?
So the reconnection happens through numerical diffusivity. Yeah.
Okay.
Yeah.
Where it's actually.
Yeah, we can mostly by looking at the numerical resistive heating, which we also write out as a 3D volume quantity, you can see there those spikes, and that is normally a good indication that the connection is happening.
How tall your speakers are compared to like the speakers, like when you look from the I think that is the next slide. So how tall these speaker like disturbances compared to what is observed?
I mean, the total scale is here something like 100 megameters, so you kind of can get some idea. So some of the stuff is 10 megameters down here, some goes a little higher.
What am I seeing right there? I see different. I see a checker box, checkerboard. So 179, 193, 211.
Yeah. So yeah, it's a different AIA channels. The top one just shows the top ones here, 170, 190, 193, and 211 without running difference. And then the other ones, the other 6 are running differences for all the AIA channels.
So each actually, how's the grid? I guess each part of getting feedback from the upper corona to the lower hemisphere also. It's one both ways, or is it just?
I mean, by eye, you see mostly upper traffic stuff, but I'm pretty sure if you do a careful filtering, you can only figure out the other part as well. It's just nobody looked at it in detail. This is quite sun, and then just, of course, we have also Corona set up. This is actually from Anna Pachenko's paper, and I mean, already this was shown in the morning. And so these are actually a couple of active regions, and the 2 of those figures are actually withMURaM, the rest are observations. And the withMURaM here is the panel E in both of them, kind of give you an idea. I mean, in general terms, it seem to get corona loops. And what Annie showed in her paper is that the underlying emission structure is not necessarily that you see individual compact loops in the corona. It's a more complicated density structure, which in general is certainly aligned with the magnetic field, but the cross section is more complicated, and what really makes the loops you see these are more line of sight integration effects, depending on whether you integrate, if your array is aligned with an extended high density region, if you just look through it in a kind of, if you have a, for example, if you have a density region which is more elongated in the vertical direction, then you look just straight through it, you get very little emission. But if you would look from another direction, where you look along it, you get see a peak in the emission. And and any kind of describes this more as it's like a veil, a curtain. And you look basically through this curtain, and sometimes the curtain looks more thick because you kind of look along the ring rather than just through it. So in that sense, the simulation could be helpful to investigate how rather complicated cross-section impact certain line of sight integration effects. And then we have been doing also quite a few active region setups. This is just an example of a very recent simulation which was inspired by AR1115A, where we essentially set sunspots on the collision course. And this is the first simulation where we actually successfully produced an X5.6 flare. And the bottom panel shows here actually the computed soft X-ray emission. So you can, from these simulations, compute soft X-ray and classify based on that. And this is also the first simulation we ran 100% on GPUs. So that is getting on the go with this in the future. And there was a big team effort behind it, of course, getting the code running on GPUs. In the next figure, this is the same simulation, but what I did here is I computed something which is maybe a little bit of proxy of what we can get from instruments like UConn, but here I did it for the ARA 171 line. And this is the left panels, I show the emission, then the middle panels here show the emission weighted line of sight velocity for the three grid direction of the code, and the right panel show the emission weighted RMS velocity. And in the end, we see the flare goes off, and then of course this goes all through the roof. But you see, for example, some effects like that in the core of the active region, you actually see some reduction in the RMS velocity, and you actually see more of the RMS, which would be the non-thermal line width outside the active region core. Of course, this is a very crude way. You could do this also the proper way, starting with a 3D cube and really computing the full line, including all the effects you need to consider. So this was just a very rough overview of what is in principle out there. So I do have various models, quite some. There's also some corona models we computed where we just added something like 5 Gauss to a quiet sun simulation, and then various active region models, including flux emergence models. And the data I have, it's typical low cadence 3D cubes and then high cadence emission measure and emission measure weighted line of sight and RMS velocities, as well as high cadence 2D slices through various parts of the domain. So if you want to look at any of these models, I'm happy to share the data I am having. So as I mentioned, there are some limitations. Most of these models are more local domain, but they have relatively high resolution for a corona model. So it's very good to explore line of sight integration effects. But most of these simulations were not computed with seismology in mind. That means the time cadence of the 3D cubes is likely not as high as you want them if you really want to do full forward modeling. And they have this Alfvén velocity cutoff. I would have to check carefully if that is limiting. It wouldn't be too difficult to just rerun some of these models and set these cutoff just at a high enough level where it wouldn't impact anything. And yeah, I'm also open to suggestions. If there's anything specific you need, let me know. And if we do some new simulations in the future, I could try to actually accommodate that to the degree it's possible. So the 2D is really high, the 3D cubes. I mean, we have typically for this simulation, we have a variable time cadence, so it depends a little bit, but let me. I mean, for more quiescent corona, I would say something around 200 seconds. If a flare goes off, the time cadence goes down, then time cadence is much better. But I guess for any sort of wave studies, you likely don't need the high time cadence for a very long time. So could we run something for a short time with higher cadence, also set the arcane velocity cut off a little bit higher? Actually, I do for relatively simple active region setup, I have already something like that.
I mean, typically for coronal seismology, we use the 30-second cadence, which, you know, for an hour,
Yeah.
something like that.
Yeah.
So you might have something already.
Yeah, at least for one run, I have something like this. And for others, I'll keep it just with something.
How much your granular size depends on your bit size?
Like-
Yeah, so if you would go for like twice the resolution.
So the resolution of about 200 kilometers horizontal, that is kind of the lowest resolution we can do before we lose correlation. But if I go to a grid size of 400 kilometers, you have convection cells twice the size of granules. That would be your dominant mode of convection. The core always kind of forms the smallest convection cell it can form on the grid you get. But if it goes to higher resolution, you don't get smaller granules because there are some intrinsic physical processes which just prefer the granulation scale in the photosphere. But if you under-resolve it, essentially you get mesogranulation, you just push it out there.
So I guess when you look at these small scale events or any type of feature, you see, and compare it to data, things like reconnection rates or
Yeah.
even time scales, it gets similar. So,
I mean, in terms of reconnection rates, I mean, I looked at this for just some of the stronger players. So if you look, then go to the current sheet and look what is the inflow into the current sheet in relative to the RPM velocity, you get something around 5% of the RPM velocity. So what people typically find.
it's only, it's usually,
Yeah, I mean, what we did is we tuned the numerical diffusivity to capture at least a little bit the behavior of the corona, so they are tuned to operate in a high magnetic quantum number regime, which means the numerical resistivity is lower than the viscosity. And so we actually have a very intermittent numerical resistivity. If the solution is sufficiently smooth, it's disable. Only if currents see the thresholds, then numerical resistivity kicks in and allows for the connection. But since it's in a high quantum number regime, what it means is when you actually have reconnection, the resistive heating is small, and most of the energy is released by the Lorentz force driving outflows. And then that kinetic energy is then thermalized through viscosity, which is large. And that's actually what the corona is doing as well. And if you use Spitzer values, the viscosity of the corona is something like 10 to the 13 centimeters squared per second, which is actually not that much different than the numerical viscosity we have in the cone like this. It's just the resistivity we can't get as small as it is.
Is there a simple explanation for an instrument person like myself to understand numerical viscosity and how that induces reconnection?
I mean, it's the numerical resistivity, but it's kind of the general problem. I mean, you have these nonlinear equations which always produce structures at smaller and smaller and smaller scales. And at some point, you have, at the grid scale, all this energy would accumulate. If you don't remove it, the code would become unstable and blow up. So you have to put in some resistive terms, which diffusive terms, which removes this energy at the scale of the grid. And these are these numerical diffusivities.
Okay, and how is that connected then to reconnection per se?
I mean, it is the numerical resistivity. I mean, you need to break ideal MHD to allow reconnection. It's not a physical term, some physical resistivity. It's just something the numerical scheme decides based on how smooth or how rough the solution has. The scheme kind of decides in which location it needs to have difficulty to stabilize the code. So what happens is you build up current sheets, and when these currents see the threshold, there's a risk that the code actually becomes numerically unstable, then at some point the code switches to a more diffusive regime. So that also allows in those regions reconnection.
So it basically takes those currents and turns them into heating.
Yeah,
You're calling that reconnection, letting them just know like.
yeah.
So you're just basically shorting out those currents through a resistor
Yeah,
and then creating.
yeah.
heating.
Actually, most of the energy is then released after you reconnect it. You have basically these retracting loops from the reconnection side. So the Lorentz was actually accelerating flows. That is how most of the energy is released. But that has to do with the high quantum number regime, that we run the code in the regime that its stability is much lower than its cost. And the formal quantum number of the corona, at least for moderate temperatures, like maybe 2 million Kelvin, if you use pizza rate, is about 10 to the 10.
Thank you.